floor. And Ms. Deepthi, the stage is all yours now. You can please go on. Thank you.
Yeah. Hello everyone. Good afternoon, distinguished speaker, presenter, delegates, and my colleagues are present here in this session. It's my great pleasure to welcome you all on to the session on application of functional safety principles at software and hardware levels. I, Ms. Deepthi Dubal from TÜVSÜD South Asia, will be your session chair today. And I must say this is a great pleasure and great honor to me. This is really a glorious moment to extend my warm wishes to SAE on behalf of TÜVSÜD South Asia for organizing this very wonderful and the first functional safety conference for our India community. When we started this journey, we saw that lots of people are, sending their interest to present the papers. And it is really my heartfelt gratitude to all of you, all of the participant and presenter out here. It's my immense pleasure to walk you through and introduce you to the presenter from various organizations like Robert Bosch and Maruti Suzuki, and appreciating their efforts for working on this topic. The session will be started by Mr. Abhay Konje and Mr. Navalkar Varadkrishna from Robert Bosch, and then who will be presenting paper on handling freedom from interference from mixed criticality system. Followed by Mr. Mudit Gupta from Maruti Suzuki, who will be presenting his paper on functional safety methodologies using model coverage analysis as a tool for requirement optimization in a model-based software development environment of automotive EE system. And the third paper will be on software safety analysis, will be presented by Mr. Shashank from Engineering again. In the best favor of time, we will be request our presenter to limit their presentation to 20 minutes, and then we have a platform open for the participant for question and answer for 10 minutes. With this, I would like to invite Mr. Abhay Konje and Mr. Varadkrishna to present their paper on handling freedom from interference in mixed criticality system. As the topic revolves under the current trend in automotive such as connectivity, autonomous electrification, and shared mobility are triggered an exponential growth in complexities of associated system with respect to SOC. Now over to Abhay and Krishna.
Thank you, Deepthi.
Bharat here. Yeah. So I will just start sharing my screen.
Yes. Yes. Yeah.
Is my screen audible? Is my screen seen?
Yes, you're audible.
My screen is seen. You can see the presentation.
Yeah.
One second.
Okay. Not for me.
Yes, your screen is visible.
Okay, so you can see the presentation, right?
Yeah.
Okay, thank you. So good afternoon, everybody. So myself, Varad, and my colleague Abhay, we are from the functional safety team for the ADAS at Bosch. And to start, before we start with the topic, I would like to thank SAE India and the organizing committee for providing us this platform to present our topic. And yes, I then straight away go into this topic, handling freedom from interference in mixed criticality applications. To begin with the agenda, we will start with what are the upcoming trends that we see in the automotive industry. And with these upcoming trends, what is the complexity we see with hardware and software? And with these new architectures coming in, what are the challenges that we see to implement freedom from interference solutions? What are the fault modes that we need to address for the FFI? And finally, we would also have a look at some of the solutions to implement freedom from interference in such systems. Okay. So the trends that we see or in the coming years are we will have electrification, we will have connectivity, shared mobility, autonomous driving, and of course artificial intelligence. These all functionalities will bring in a lot of complexities, and what I would like to focus is all these functionalities would need a lot of processing power. And that brings me to the next topic, how our architecture or an ECU would look like. So unlike our conventional systems, which only a single microcontroller, for the systems that we are speaking currently, we would have SoCs. That means a lot of system on chips. SoC system on chip, which would have a lot of CPUs, maybe up to 8 to 10 CPUs, and then we would have these GPUs and the DLAs, that is the graphical processing units and deep learning accelerators. So why do we need these? For example, for the autonomous, we would need perception algorithms, and these perception algorithms would need a lot of deep neural networks. And to implement these deep neural networks, we would have the processing power, which is supported by GPUs, which would support parallel computing. This GPU could have up to 12 cores in it. And if there are any complex operations that would be needed, such as convolution, then these can be offloaded from the CPU, and then the GPU could do a lot of such parallel computations. That means there are a lot of parallel multiplications and additions these 512 cores are going to process, and then they are going to return it to the main CPU. Of course, we also have the deep learning accelerators, and this itself, the GPU which is on the chip itself may not be sufficient, the processing power, that is what we foresee, and we would also have an external GPU. So apart from this processor, we would continue to also have the microcontroller in these advanced systems that we are talking of, and the various other ASICs. And the communication between the various processing elements would need, again, a lot of high-speed communication channels. So this is the architecture that we are looking forward for the new generation ECUs. And with this, I move to the software architecture, a brief software architecture. So as I said, we would continue to have a microcontroller and microprocessor together in these systems. A microcontroller employed as a master and microprocessor as a slave. So most of our conventional ECUs, we are familiar with this left side architecture. We would have a number of cores on this microcontroller, of course, with a lot of inbuilt safety mechanisms. We would have the boot layers, we would have the MCAL and the classic AUTOSAR software. And the AUTOSAR based on the OSIC standards, the RTE, and the application software. So more or less, this is similar to what we have in our conventional ECUs. But on the right side, when we move to the processor world, we have a lot of new elements coming into picture here. We are having a n number of cores, and as I mentioned, we have GPU. There will be a boot manager layer, and we see this hypervisor layer. So what is this hypervisor layer? It would support a lot of virtualization, wherein you can have virtualization of operating systems or virtualization of various software components. So there could be more than one operating system which runs on top of the hypervisor. That is the trend that we see. And the operating systems for the processor world would be based on POSIX. An example is QNX from BlackBerry. So these are all the new generation topics that we see. And on top of this, we have the adaptive AUTOSAR for the microprocessor world. and over on top of the GPU, we see the CUDA layer. So CUDA is just like a middleware for this GPU parallel computing that we talked about. And of course, the external GPU would also need such CUDA interfaces. So, and on top of this, application software. So this is just a very brief the blocks that we see in actual practice. This is much more complex. We will have a lot of stakeholders or a lot of suppliers who provide their software, a lot of intellectual property software that come from these various suppliers, which are not represented in this diagram. But what I mean to say is it would be much more complex than this diagram. And when we complexity, we have the software from the different suppliers, and they will be at different SL levels. So for representation purposes, we have shown it as X, Y, Z. So basically QM to SLD, we will have a lot of different SLs for these various components which are distributed here and there. And that is what we call as the mixed criticality system. So this is how the complexity of the mixed criticality system for maybe an autonomous driving would typically look like. And with this architecture being explained, the hardware and the software, how it is, what are the challenges that we have from the implementing the freedom from interference in such systems. So we have, as I mentioned, software from multiple suppliers with different criticality QM to SLD. That itself is a very complex topic. Then when it comes to the processors, there are going to be a lot of shared resources that we have in these processors, and the processes are going to share a lot of shared resources. I will briefly also cover what are the shared resources which typically would look like in an processor. Then we have the communication between the various processes which are distributed across the processor cores. And as I mentioned, the complex operation which would be offloaded from the main CPU to the GPU, there would be a lot of resource and process sharing. When the CPU itself offloads certain operations to the GPU, then it would also mean that because these are safety critical processes that we are talking of, it should be executed within a time. So we have to also consider the worst case execution time that is required, and this also adds to the complexity. And then we have this as CPU have memory traffic, and in a processor we are only having a single external RAM in most of the cases. And then of course we also have to deal with the communication aspects between the various execution elements that I showed you, between the processor itself and also between the processor and controller. Talking a little bit about the shared resources, maybe as one reference architecture, what are the shared resources which would look like in a processor. For example, in this architecture, we are having 4 clusters, and each cluster has 2 cores. Every core may have its own L1 cache, and these 2 cores are sharing L2 cache. Similarly, this whole cluster and the GPU that I talked will share a common cache, L3 cache. So this has a 3-level cache architecture. Of course, to deal with such caches, which multiple levels of caches, we have a lot of interferences that arise due to caches. This itself is a research topic in itself. What are the various interferences that arise in the caches, and what are the solutions? Of course, due to the shortage of time, we cannot cover all this. But what I would like to focus is the freedom from interference in such systems is a very complex topic, and we are just giving you a very short summary. But there is a lot of potential in this topic, which has a lot of research focus, and also some ideas from avionics, because avionics is very extensively using some of these technologies can be used, and also we are working towards. So that is what I wanted to focus here. And the DRAM bank, that is the external memory, as I said, because we are dealing with processor, it's a common DRAM bank that is also shared among all the execution elements. So with this brief introduction about the key challenges of freedom from interference, now I would like to talk about the fault modes. I think most of you who work on the safety topics would know this. that these fault modes are covered in the part 6 of the ISO 26262. So for what are the fault modes from the timing that we have to consider for the FFI, blocking of execution. For example, a lower level safety software due to any fault could block the execution of a safety critical software. There could be deadlocks, there could be live locks, which could block the execution of a safety critical software. There could be issues with the OS, incorrect allocation of execution time, and incorrect synchronization between software elements. So these are the timing related issues. Mostly we refer them as the temporal issues. Next, the memory itself, because the memory is a shared resource, there could be corruption of memory due to faults in this software components which are not developed at a high safety level. There could be inconsistent data, there could be stack issues, or there could be unintended read or write access to certain memory which is not permitted. So these form the special issues. And then for the communication channels between the various elements, we have to consider the various fault modes which are listed here: repetition of information, loss of information, delay, insertion, masquerading, incorrect sequencing, corruption, asymmetric information, or information from sender received, which is received only by subset of receivers, or a blocked access. So these are some of the fault modes that we need to consider for implementing the solutions. So with this, we need to look at what are the various solutions, and I will hand over the presentation to Abhay, who will take you forward. Over to you, Abhay.
Thanks, Varun. So is it visible? It's visible to all?
Visible, but make it on a presentation mode, please, Abhay.
Yeah.
Yeah.
Okay, then going ahead with what Varun just explained us was the different types of systems and different type of criticalities which may occur in the upcoming trends. Now going ahead, let's assume we have a critical application wherein we have different cores and we want to allocate the different applications across the cores. Then what can be the common constraints that we need to face out over there would be the common cause failures, which are basically the core faults, which would rise from the functions being allocated into the same group, and then allocation of the functions and its monitoring core also to the same group would be a major reason for us for the common cause failures. The next thing that we typically look at would be the software criticality, in which we have allocating the functions of different criticalities into the same partitionings. And one more thing which we want to look at is the reused functionalities and function calling, and its calling in the same partitions. This would typically result into some applications wherein there would be interferences, and this would typically be software criticality issues for us. And last but not the least, something that we would really like to avoid would be the occurrence of the cascading failures, wherein we have different functions having the same coupling, having strong coupling factors and on the different partitions, which would result into a cascading failure among them. In case if there is a failure among one of them, this would surely lead to a cascading failure onto the other partitions as well. And the second thing that would really like to highlight was the prevention of the inter-partitioning coupling, so that we have a very high degree of coupling between the intra-partitionings also. And third thing that we would like to see that the control flow cannot exist between the two partitions. So this is something that would be a problematic scenario for us. And this is what we would like to avoid in the applications using multiple cores, or rather distributed across different cores. So this is what one part of it. Then going next, we would like to come to the topic of the freedom from interference, which is the core topic that we need to address. Then typically we have found that there can be different possible methods for it. These different possible methods have their own trade-offs, rather, which have some positive points and some negative points, but we have evaluated two of them. The first one was the typical use of the partitioning method, and the second one is the use of an hypervisor. There can be other methods which are used by different domains, but due to the application constraints, we have not evaluated them. So typically we start with the conventional method of the partitioning, which are the spatial partitioning. So let's assume we have different cores with us or core partitions. So we have partition A, partition B, partition C and D, which consists of different cores internally. And then one of the best methods for partitions or recommended methods for them would be to partition the processes as per the ASIL levels, and not to have processes across the different ASIL levels on the same core. So here typically you can see we have assigned different processes to different cores based on their ASIL ratings. So this will allow us to have a reduced
Hello, Abhay.
Issues. That's why it's
Hello,
getting
Abhay.
delayed.
Yes.
condition. The next part that we can see is the spatial and temporal partitioning. Paran? Hello?
Hello, yes, Abhay.
Yes, sir. There is some interruption.
Interruption from your side, Abhay.
Processor based and the
Yeah,
microcontroller based.
due to low bandwidth, there is
Yeah.
issues from your end,
Hello?
Abhay. There is a bandwidth issues, network bandwidth issues.
You may switch
Okay,
off your
then
video.
I have to be still with it.
Yeah, for the time being, you can switch off your video, and then question answer, you can make your video on.
So is it fine now?
Better now, yes. Please go ahead, Abhay. Hello. Hello. Hello.
Hello? Hello, is it audible?
Yes, Abhay, now it is audible.
Yes. Okay. Then there would be, if you consider typical processor-based systems in which there would be an MMU, which needs to be exclusively used for the partitioning methods. And then if you take the same approach for the controller-based methods, then we have the use of MPU, which needs to be configured and extensively used. Then the second point that we found was the software of the same ASIL can be configured in the same processes also, OS processes also. This would lead to the avoidance of unrequired dependencies between the different processes. And then next point we found that the objects and libraries that constitute a process shall have the same ASIL ratings. Having different ASIL ratings, libraries or objects within the same process shall result into undue interferences between each other. And one more thing would be, if we find that priority driven scheduling is used, then process and threads aligned to assigned shall ensure determinism, so that we don't have uncertainty with respect to the priorities of the processes that are going to appear in the system. Now going to the microcontroller based system, use of program flow monitoring and external watchdog is typically suggested, which will ensure that critical tasks are not missed by any means. And the timing protection for the timing protection budget and OS tasks shall be enabled by configuring the following budget values. These timing values shall be the execution budget time, which would be the typical maximum amount of time a task is allowed to execute, resources allocation to the budget, and the intra-arrival time budget for the task. Then the next thing that we have would be the end-to-end protection for the system. In a classical AUTOSAR based architecture, we have the end-to-end protection library, which is AUTOSAR E2E library, which can typically be used to avoid interferences when data is being communicated across different processes. This typical library allows us to transmit safety rated data and also to receive them with an error correction and error detection mechanisms inbuilt to them. The next thing that is typically that we have tried to explore was the hypervisors mechanism from freedom from interferences. But typically hypervisor supporting the SOCs can be used as a mechanisms to fulfill the freedom from interference requirement as per ISO. Virtual machines with mixed criticalities can be easily facilitated by the use of an hypervisor. Typically, a hypervisor supports the different mechanisms using the MPU to provide a spatial partitioning internally. And we typically feel that further investigations are needed for using the hypervisor in critical applications wherein resources are a real constraint, maybe such as the automotive domain for us. And this was the part. This is all we had from the two methods that we have investigated, and would rather like to have more of questions from you now.
Very well done, and very huge round applause to Abhay and Bharat. Now, audience, it's time to you for the question. Is there any question to Abhay and Bharat? Hello, Suraj, if you can provide questions here.
Yes, ma'am. We'll just post the questions here.
Yeah.
So we have posted the first question.
So there is a question from Pradeep. So in the case that I'm designing a system where all the components are of the same ASIL level, is it not required to prove FFI of my system? Can I tailor that requirement in my development flow? If you can provide your answer, Pradeep, sorry, Bharat, Abhay.
Yeah, typically if you have a system wherein you have everything at the same ASIL rated, then you need not have FFI because all the things are having the same integrity level, and the development of the systems would be done in such a way that none of them would be interfering with the other parts of it. So if everything is of the same ASIL, then you don't need FFI. That's the basic ruling that, or the basic principle given in ISO. If you have multiple ASILs, only then you need an FFI, or else no. Pradeep, I hope that answers the question.
Yes. So now from Manohar, there is. if you can see Abhay or Varad, would you like to respond that?
Yeah. So here I think the question is about the cores and the partition. So this is just with reference to the architecture that we have showed. Here in the one cluster of the processor had two cores. And because they were sharing the same level of cache, we decided to have one common partition for those two cores. That is what it means, partition A for core 0 and 1. Because they share the same level of cache, we made it as a single partition.
And the next question is with respect to slide number 7. I could not get that question.
There is from Jagdish. The question is: do freedom from interference address the common cause failure?
Yes, we have to consider the common cause failures while designing the solutions from freedom from interference. That is right.
Freedom for interference would only provide you a relief from what you're going to do to the interactions. But if there's a common cause which is going to affect both the applications or rather both the processes, then that surely needs to be addressed independently also.
Yes, there is a question from Anup from slide 7.
I could not see the question, but
I
I
could not say. I
We
can
could not see
read it for
mention
you.
of encryption, decryption between each layer in slide 7.
we have, for the reason of complex simplicity, we have omitted all these things. But typically, the system should have inbuilt encryption and decryptions to provide the communication errors. That the end-to-end protection should be there when we transfer data from one block to another block. Of course, this would add to your complexities, but considering the criticalities in a higher ASIL, it's desirable to have these type of protections.
Okay, there is one more question from Shilpa. Can you please brief on hypervisor mode?
Varad would like to take it up.
Yeah. So a hypervisor would typically be a layer which is on top of an SoC, or also it can be on top of a controller. And this hypervisor would then support you to implement a lot of virtual machines. The virtualization can be of anything. It can be of the software, or it can be multiple operating systems that would run on top of the hypervisor. So it hypervisor would then employ the various hardware solutions such as MMU, and thus in turn it can be used as a solution to implement freedom from interference.
There is yes, one more question is what are the systematic technique to prove FFI in processor? Any qualitative or quantitative technique? Or
Currently,
you can yeah, please.
Yeah, currently we prove it by just analysis of the different processes and the different resources that are being used, and also how are we partitioning them or rather allocating them. But as of now, we are not aware that there is any tool which can give an exact figure for this in terms of qualitative.
Yeah.
Sorry, in terms of quantitative.
Yeah. So as I mentioned, this is a very, very evolving topic, and yeah, a lot of research needs to be put in to further work on. So this is still, all these are open topics. Yes. I think there is one more question. Are these methods recommended by ISO standard? No, the ISO standard does not talk about the specific methodology. These are to be investigated. The ISO standard as such only talks about the failure modes, but not in detail about what are the various solutions that we need to have.
ISO just provides us a guidelines what methods technically need to be implemented, have to be decided based on the different applications and also the different types of processes that we are going to follow for them.
Okay, there is one more question from Yutika. You can see, yes, there was a glitch. Can spatial or temporal partitioning be explained again? Abhay, which is there was some glitch. Yeah.
Okay, so typically what you do in a temporal partitioning is you try to see that whatever processes are run across processes are being run, different processes, these do not interfere into them for the timing constraints of it. And for the spatial partitioning, what we try is that whatever memory allocations have been done for the different processes, these do not overlap into each other. Now let's take the example for the spatial partitioning part of it, wherein we have to ensure that the memories of the different ASIL do not overlap into each other. For this, typically the processor has the MMU, which can be utilized very efficiently to allocate the different space in memory for the processing different processes. And if we go exactly on the same lines for the processor, then processor has an MPU unit which can be taken up and we can use it effectively. So by doing this, we can ensure that we have spatial partitioning possible in MPU, microcontroller also, and the microprocessor based systems also. Typically, then second part is that if we have different ASILs rated, then we can have the same ASIL rated systems or the components in a same segment, or these can be taken up in the same OS process also, because these have the same integrity level with them. Again, one more recommended point was that whatever libraries or objects are there which constitute a process shall have the same ASIL rating. So let's assume we have different parts of the process, and if we have different A and B ASILs put together, then it's not recommended to have different ASIL rating working together in a common process out of it. And the last point we have was for the scheduling part of it. If you have scheduling which is dynamic in nature, then you should have a deterministic method to allocate or to predict that which things would come up at what instance of time and how do you manage the priorities for them. So that a process with a lower priority does not go and occupy the system when a system or a process, when a process with a higher priority has to get the access of the system. And of course, the final point is the timing budget, which we have to take care so that we don't overlap into each other's processes.
So, considering the time, we can take one more question. If you would like to take up, Abhay or Bharat?
Yes, we can. If you have
Yes,
time
yeah.
permits, then fine. Yes, yeah.
Yeah, one question we can take, and then we switch over to another presentation.
So which question? Maybe you can choose the question because there are many in the.
Yeah, can we need to show FFI at a signal level? A question from Sushil.
What is signal level is not understood clearly. Sorry for that.
Okay. Yeah. So that is perfectly fine now. This is again, a great work by Abhay and Bharat. Thank you very much for an enlightening presentation on both the topic, which is very clarified on various concepts. And freedom from interference can be achieved through various different methods and by using partition software and hardware-based solutions. So great job. Now, but this time I would like to invite our
Thank you.
Thank
other
you.
guest. Thank you. Thank you very much. Thanks again.
Thank you.
It's very well done. Yep. Because we are virtually, we cannot do round of applause. Yeah. So now let's move from the giant supplier to giant OEM. Now it's time from going forward from the presentation to Maruti Suzuki. I am delighted to welcome Mr. Mudit Gupta from Maruti Suzuki on presenting on his topic on functional safety methodologies using model coverage analysis as a tool for requirement optimization in a model-based software development environment of an automotive EE subsystem. As this topic is also revolving around functional safety, ISO 26262 Part 6, unit testing, model code coverage, and requirement engineering. So now over to Mudit, your time starts.
Hi, good afternoon, everyone. This is Madhur from Maruti Suzuki India Limited. And please let me know once my screen is visible.
Yes, we can see you. And now this is on presentation mode. Yes.
Okay, so good afternoon, everyone, once again. So the topic for today's paper from our side is using model-based coverage analysis as a tool for front-loading requirement optimization, as mentioned in ISO 26262. So basically, this is regarding improving the functional safety starting from the requirement stage itself. So when we look at the goals of functional safety, there are two main goals. One is avoidance of fault, which is during the designing phase and during the development of the software and whether the defining of the specifications. And the other part is during the actual execution to control the failures. And at that point, we see the error diagnostics come into place. And if we define risk, it is mostly because of the unexpected failures. That could be, if we want to quantize those, it would be the higher the severity, the lower the controllability, and the higher the frequency of the failure, there's more chance of risk occurring in the system. And if we try to define it graphically, as you can see, there's a hyperbola curve where if the severity is too high and the probability of its occurrence is also high, then we could say that the risk is quite unacceptable. But on the other hand, if we could try to reduce the severity of the risk and if the probability of the occurrence of the risk could also be reduced, then we could probably define it as something as acceptable risk when designing the system. And moving further, so what is actually risk when we come to software design and development? As per the part 6 of the ISO 26262, there are various stages and there are various concepts through which we define the risk and how do we control those things. So if we look into the specification part 6, the part that we are most concerned about is the specification of software safety requirements, which deals that the software development should be suitable, it should be compliant to the technical safety requirements, and it should be consistent with the hardware-software interface. And further taking a deep down into this particular aspect, so the suitability of the software development is defined. It's that when the software is developed, it should be unambiguous, it should be comprehensible, the requirements should be atomic in nature, it should be implementation free, means it should not be platform specific, and those should be verifiable, conforming to the standards. It should be feasible and achievable. It should be complete in itself. Only the necessary requirements should be part of the actual development, and it should be consistent, internally consistent. So these are probably the requirements there, but in today's aspect, in today's paper, we are going to see how we are going to achieve more into the feasibility aspect, the completeness, the necessity, and the consistency part of it. So if we see how do we actually improve the requirements. So right now we are looking into the process where we could front load the process of the requirements with the model coverage part itself. So looking into the classical way of designing the requirements is like it's basically a manual process of defining the logical requirements. There's no mathematical validation as of now, and it's only a manual review that is done to improve the requirements. This basically is may not be sufficient to catch all the impacts or the defects that could lead into the further failure of the software or to a reduced risk level. Now, when we talk about the model coverage, model coverage basically deals with the completeness of the test cases which is required to check the developed software, and it highlights the undesired requirement. And how do we actually do that if we look into the basic aspects of what all kinds of model coverages are there? So there are 4 types of model coverages. One is the execution coverage, which determines whether this item is executed during simulation or not. The decision coverage, which determines that the percentage of the total number of simulation paths that the decision paths. The conditional coverage, which requires all the inputs to the logical blocks to be true and false at least once during the compilation of the simulation, and the modified condition decision coverage, which defines the coverage checks for independent effect of an input on the outputs. So taking some examples, like the first example, if we consider a scenario where a requirement is defined in two clauses, where the output would be true if both the clauses are true, at least either of the clauses true. Then if we see the clause 1 determines, let's say for an example, the output would be true if any of the car door goes from closed to open. And the clause 2 determines if any of the door is open and any other door goes close to open. So if we take just the clause 1, then we can define the system in this manner, where we take the input from all the doors, we take its previous state and the current state to determine that it has gone from close to open. And if those outputs are true, then we say that the final output is also true. And coming to the clause 2, where it is basically if any of the door is open, which is the lower part of this system, and any other door goes from close to open. So this is the system which again takes the input from the previous clause. So this model actually represents this particular requirement. But if we look closely, then if we do the coverage analysis, then we can find out that the shaded area or the lower part, or basically which is the one of the part of the clause 2, is not even being covered. So even if it is not implemented, it will not lead to any kind of fault in the logic. So why is it so? So to understand that, let's break down our clause into further conditions. Let's say if the clause 1 is condition 1 and clause 2 is broken down into two subconditions. The first condition is, of course, any of the door goes close to open. The second condition, which is the first condition of clause 2, is if any of the door is open. And the condition 3, which is the second subcondition of the clause 2, if any other door goes close to open. So if we closely look at the condition 1 and condition 3 are quite similar. And so if the output is condition 1 or of and of condition 2 and condition 3. So if we replace condition 3 by condition 1, since both are similar, we find that only output is directly linked to condition 1. There's no dependency on clause 2. So it looks like the clause 2 is not required at all. So it can be removed. And the desired output can be obtained by using clause 1 only. So moving on to the next example. So we take another scenario in which, let's say, a state variable can assume two states, say state A and state B. When state variable is in the state A, then the output is this following output pulse. So where a ramp up happens for a certain duration, then it reaches its 100% capacity for a certain duration, and then a ramp down happens. Okay, and then going to the next clause of the requirement, if state variable is at state A, then after 20 seconds, state changes to B. Okay, so if we try to implement, let's say, first the first condition and then the second condition. So what happens in this scenario is, using this model coverage, we can determine that only if the first part or the state A is implemented, then the ramp up will happen, and within 20 seconds, let me try to move this. If the ramp up happens and the 100% part is achieved, this happens within the first 20 seconds itself. And the model works quite fluently with this logic. But if you see the part where the ramp down is required, that does not execute at all, because we have covered our system within the first 20 seconds itself. And so the ramp down is not taken care by the system itself. What happens is, then we come to the next state where it says the ramp down also has to happen, which is defined by the state when it changes to state B. This again is to be taken care by the state B variable. So the first part where the ramp down is to be taken care in state A is not executed at all. And this is what is found through model coverage, that if we do not have this particular requirement in the state A, rather it is only contained in state B, that would also suffice the requirement. So what does this summarize? It leads to that using model coverage analysis, we are able to improve the requirements to gain few of the characteristics that are described in ISO 26262, part 6 and part 8. So if we see the examples, the model now becomes more feasible with the requirements becoming more achievable. The requirements are more complete. It has only the necessary requirements, and those are internally consistent. So this improves the requirements by this approach, and it can front load to find the infeasible and redundant requirements quite early in the development cycle. So basically, once the requirements are defined, a model is created to find whether those requirements are being covered completely using all the model coverage approaches. If any of the approaches or any of the model coverage approaches leading to some unambiguous or incomplete or unnecessary requirement, then those can be taken as a feedback to the requirement itself to improve those requirements. And this is how it would lead to catch the any kind of infeasible or unnecessary requirements at the much early in the development cycle. So this is all from our side, and please let us know if there is any question. Hello.
Yeah, thanks a lot, Mudit. And
Thank
it is very, very well appreciated that you have presented and justified the topic. And it is seen that there is too much research on the topic. So now time for the audience for a question. So we are exporting the questions. So we'll wait here for a few minutes. Suraj? Hello, Suraj? Yes.
Yes, ma'am. We're posting it one by one.
Yeah. Okay. Yeah. Thanks a lot. There is a question now for you, Mudit. Are you using any requirements management tool to take care of all such requirements?
So right now, though we are not using, though we plan to use something like DOS or something, but as of now, there's no such tool to do it. We actually do the manual review of the requirement, and that is how it is taken forward.
இது எல்லாம் நோட் பண்ணிக்கோங்க பாயிண்ட்லாம் இங்க அந்த क्वेश्चन விட்டுச்சு ஏன்னா
Hello. Yes.
Sorry.
Yes. There was a little disturbance. Now we have a second question also. Can model-based approach be used for hardware requirements?
To look into it, see, when we are talking about this particular approach, I'm not pretty sure this could be the thing, because when we talk about the model, it's mostly about the logical requirements that are being implemented and the flow of the necessary and the conditional requirements is being checked. When it comes to hardware requirements, this may not be the right approach to check and front load the requirements with such procedure. Because with hardware, it is not more sort of a logical issue, it is more issue, and this may not be caught at the coverage level.
Okay. There is one more question from Ashwini. How to maintain the traceability when the requirements are covered using model coverage?
So traceability is as such the part of the first question itself to the requirement management of certain tools such as DOS. I'm not sponsoring taking any tools, but just an example, anything like DOS or something can be used to trace the requirements, and also change request management could also be used to link to the requirements management tool.
Yeah, again, people are asking for the tools.
Yeah, I can give certain examples, of course. So if to name very specific tools, there are tools from MathWorks, and then there are tools from ETAS. The MathWorks tool is the model coverage based analysis tool, and from ETAS, it's ASCII-based test tool. So these can be used, and there may be other tools also, but these are some things that we have actually used. So if there's any other question.
Yeah. The question Yeah.
I don't think there's any more
Yes.
questions anymore.
Yes.
I think we can wrap
Yeah, we
up
can
this.
move.
Sure. Thank you. Thank you everyone for your
Thank
time.
you. Thank you. Thanks a lot. Thanks a lot, Mudit, for your time. Now, we have a very interesting paper rounds are going on in session 2. And the presenters have given very elaborative information. Now let's move from freedom from interference to model coverage analysis. And now it's time to move to software safety analysis. So I would like to invite Mr. Shashank from Robert Bosch for presenting the paper. The paper is on software safety analysis, approach by analysis of safety requirement in compliance with ISO 26262 newer version of the standard. So over to you, Shashank.
So hi Deepti, hi everyone,
Yes.
good afternoon, good evening. So let me start presenting my screen. Let me know once you can see the screen. So meanwhile, I would like to
Yes,
say a
please.
couple of things. So thank you so much for the opportunity to present in SAE conference. And secondly, so I have devised this entire presentation in 3 ways. So anybody who's gonna talk next or listen about the software safety analysis, I want them to take at least 3 important things. So first thing is, what is software safety analysis and why ISO 26262 mandates to do software safety analysis, why it is necessary. That is the first thing. Second thing is, what is the approach? How can software safety analysis be done? There are different approaches, but what is the guidelines that is given by ISO 26262 on this? And the third part is what I want everyone to take from this is like having to do software safety analysis. What is the outcome? Why are we doing all of this exercise? So what is the outcome from this? So with that being said, let's jump straight away into agenda. So firstly, why is software safety analysis needed? What is the motivation? Then the second part would be scope and boundaries regarding specific architectural design to be analyzed. And the third part is, like I already mentioned, the second part for what I want you all to take as approach. So so approach is 2 ways. One is what approach can be defined, and the second thing is how it can be compliant with ISO 26262. What sort of guidelines do we have from ISO 26262? And then we go into what sort of inputs we need to do software safety analysis, and what are the inspiration in terms of failure mode guide words, safety mechanism, test measures from ISO 26262. So this is all the part that I've taken from ISO 26262 part 6. And finally, the last part would be so having to do software safety analysis, only one half of a thing. The second half of the thing is mitigation strategy. How do we mitigate whatever failures, whatever negative effects of software we have found out through this analysis? How do we mitigate that? That is another thing. So let's straight away jump into the first thing. What is the motivation? So let's just begin with asking ourselves a question. What is software safety analysis? So in very simple words, it's a analysis done at the software architectural level. So we have from HARA, we get requirements at the vehicle level. So OEM, for us Bosch at least, the OEM gives us a customer requirements. So then we do a system packaging where we have system safety requirements, then we further allocate hardware safety requirements and software safety requirements and so on. So software safety analysis is an analysis that is done at the architectural level of the software. So why is it necessary? The first thing why it is necessary is software is there in every safety critical system, and it is expected to behave with certain functions and certain behaviors, and it is also designed, developed, implemented, tested and validated at certain asset. Despite going through all of this stringent process, it is still, according to ISO 262, it is still possible to have an analysis process to find out whether there can be any design weaknesses or design failures, and that design failures and design faults could be mitigated using certain mitigation strategy. So the first motivation is we find out what sort of failures is possible within the design of our software. And the second part of the motivation is mitigation. So how do we mitigate is basically find out the incompleteness or inconsistency in the safety requirements. So this is basically is going to give certain value addition to our software safety concept. So we'll be able to find out whether if there are any inconsistency, can we define certain test measures to make our software more robust, or do we have to implement further more safety mechanisms or safety requirements with certain ASIL level again to make our software error free or failure free. So the next thing would be, once we know what is the motivation, so we basically know where we begin and where we want to end up. And the second part is we have to define certain scope. So also Varad and Abhay was already talking about different sort of ASIL in the software. For example, mixed ASIL, and there was also a question on max ASIL. So if my software is all of same ASIL, do I need FFI? So basically what I would say is, if your software is all of same ASIL, which is a max ASIL designs, that means all the requirements and the architecture is designed, developed, and tested with certain maximum ASIL. So in that case, what you really need is a software safety analysis, because in that way you will be able to find out what sort of failures could possibly happen and how you can mitigate that. So in very simple words, it's the scope and boundaries of a software safety analysis is at the architecture level. So every component which has got ASIL in it, we are supposed to take that components into consideration of software safety analysis. So this is the first part. So we talked about motivation. What is the scope and boundaries of the software safety analysis? Now comes the approach. So when it comes to approach, there is so many guidelines from ISO 26262, and they also say it could be a software FMEA kind of a thing, or software FTA kind of thing. It could be inductive process or directive process. So basically there is freedom on how you want to do your approach, but the whole thought of designing an approach for software safety analysis is very simple. So you know where you're starting. Your starting is you have some software architecture or software safety requirements, and you find out faults. That's where you start. And where you end up is another important thing. So what you get out of this software safety analysis, and that would be how you can make value addition to your software safety concept. So just to give what guidelines ISO 26262 says us. So you start either with your software architecture design here, or you can start with your software safety requirements. So from that, if you can find out what sort of failure is possible to happen, it is also possible to refine and improve. So this analysis is where you can find out what could possibly go wrong, or what is the negative effect, and so on. So if you find out all of that, it is also possible to refine and improve the software safety requirements. In this way, we've taken our existing software safety concept, and then we also make value additions to software safety concept itself. So it's a circle of process. So the starting point is definitely software safety requirements, and then we end up certain improvements and refinement done to software safety requirements itself. So that would be your overall goal of doing the safety analysis. Okay, so we just saw about what sort of guidelines we have from ISO 26262. So now how are we going to translate that in actual software safety analysis? So as I already mentioned, we have system safety requirements, then we allocate hardware safety requirements, and we allocate software safety requirements. Once the software safety concept is done and we specify software safety requirement, we take each and every requirement, and then we identify what sort of failure is possible in it, whether it is an input failure or a processing failure. So you can imagine in very simple way, there's a software, input can come in, and taking that input, the software is going to process something and the output is going to come out. And so there could be two kinds of failures where the input, the signals, the software input signals can be wrong, and this will lead to a negative effect on the output, or the processing, something within the processing might go wrong, and there will be a negative effect on the software. So if you take each and every software safety requirement, you either identify whether an input is causing a problem or processing is causing the problem. So then you start giving failure modes to this input signal or the processing of the requirement. So if you take an input signal, so there is already guidance from ISO 26262. There's a table, part 6, annexure E. There's a table which says what sort of potential failures can happen when it comes to input of the signals. I will talk about it in detail little later, but so you can start giving failure modes to your input signals or your processing. Once you find out what sort of failure is possible within a signal of a software, then you try to match that to what could possibly the negative effect due to this failure. So the negative effect on the output signal. So once you find out what is the negative effect on the output signal, the next thing is the cyclic process. So we have to go back to a safety concept. So what is the sort of impact we have on a software safety requirement? So this basically starts from a software safety requirement and ends with a software safety requirement. So this will tell us what sort of improvements that we can actually make. And then the next step would be to link or trace this negative effect of the safety requirement to a system level or at the vehicle level. In this process, what we can do is we can identify what sort of hazard is possible at the vehicle level. So this is also possible to find out what sort of safety goal is actually being violated due to a software failure. So this is all just one part of the software safety analysis. This is only analysis bit. Now the second part would be to talk about what sort of mitigation strategies is possible. So now that we found out what sort of failure is possible, what sort of negative effect is possible, and how it is affecting software, system, vehicle, and safety goal itself. The second part is like, so how can we make this software error free? So one could be, you can define test measures for every failure mode to find out what sort of behavior software is going to give. And in that way, we can analyze what sort of end result from this test measure is possible. And the second thing, once we find out whether the test result is not adequate enough to say for us it is safe, the next thing what we can do is we can further implement further safety mechanisms or safety measures or even safety requirements with certain ASIL level. So what this does, the entire process, what this does is basically is going to have a value addition to a safety concept. In that way, we can make, even though this is a theoretical analysis, it is still possible at the requirement phase and the conceptual phase to have a value addition to our safety concept, and we can make our software robust. Okay, so now we just talked about the approach. So how are we going to translate into some sort of tool-wise? So you can just simply put it into an Excel sheet where you start with your software safety requirements, then you identify your input signal, what is your description of the input signal, then you get your failure modes and failure description from your annexure E, part 6 annexure E, table 1. And then you just connect them, you trace them to effects at the system level or the vehicle level, and what is the sort of negative effect at the software level. And then you can also use the software safety analysis as a document of evidence to say what are all things that is already done for your software safety as well. So for example, if you have already implemented certain safety mechanism for certain requirements, you can also mention what sort of mechanism is there, whether that is adequate or not. And the next part would be to define certain safe direction or error reaction. So you already defined some failures. So if the failure happens, what could be the safe, how it should have been worked, or what should have been the error reaction. So based on this, you can define certain test measures for every failure mode so that the output of the testing should be in terms of safe direction or an error reaction. If this is not adequate enough, so that it is clear that whatever requirements we have, whatever safety mechanisms we have at this point of time, it is not sufficient enough. So in that case, we are going to have to implement certain additional safety mechanisms or additional safety requirements. So in that way, we can have a value addition to a safety concept. So once you know the motivation, once you know the approach, now you're gonna have to start doing a software safety analysis. So what are the sort of inputs you require? So basically, I already mentioned the starting point is the software safety requirements. So you should have your technical safety concept derived and software safety requirements specified. And you should have your software architecture developed. Then like I already mentioned, the scope of the analysis, what sort of components will come under analysis of the software, that has to be defined. And then the list of signals, list of input signals and its signal description will be a good point to start with. And definitely what are the inspiration that we can take from ISO 26262 in terms of failure modes, critical failures from ISO 26262, safety measures, stress measures that are being recommended by ISO 26262 as per the ASIL requirements. So these are all the inputs that are needed for software safety analysis. And just to go slightly in deeper, I already touched upon failure modes in one of my approach discussion. So I also mentioned from ISO 26262, we get a table where it actually mentions what sort of failures is possible. So how could ISO 262 come up with this? Since all the software errors is due to a systematic error, and they could come up with, theoretically they could come up with what sort of failures is possible in a software. So at a very simple, at the signal level, it is possible that there could be a late signal or a too early signal or no signal at all. So what are the deeper causes for all of this is also mentioned within the table. It could be delay of information or incorrect sequence, blocking, live logs, deadlocks, and also Abhay and Bharat also already touched upon all of these topics earlier as well. And according to ISO 262, it is also possible in software there could be every time there are requirements that is related to a certain range within how the process of the software had to happen. Let's say the requirement says certain value should be kept between 0 to minus 3.5 meter per second square. So there could be potential failures that it could potentially exceed the upper limit, or it could be lower than the lower limit as well. So, and the values could be inconsistent within the software. So ISO 26262 gives guidelines on like how certain failures like that can be taken into consideration, how it could be mitigated. And next inspiration that we can take from ISO 26262 is regarding the availability of different sort of safety mechanisms at the software level. So we have different error detection and error handling safety mechanisms for different ASIL levels. So the entire table here describes what sort of ASIL it is recommended to have, what sort of error handling and error detection methods and mechanisms. This is a slide that I just added just to give brief description of each safety mechanism. For example, we have certain error detection mechanisms like range checks, like I already mentioned about the failure, where the failure could be over the upper limit or under the lower limit. In this case, what ISO 26262 recommends is to have a range check for both input and output data. This sort of range check is recommended, I think, for all the ASIL levels. Yes, for all the ASIL levels, A, B, C, D, range checks is recommended. So based on all of this information, we can take what sort of failure is possible, what sort of safety mechanisms are available, and what is recommended for the various ASIL levels. And this will be a good input for us going into software safety analysis. And the third part, what we can take from ISO 26262 regarding software safety analysis is like what sort of ASIL levels, what sort of unit verification, and what sort of test deriving methods have been recommended by the ISO 26262. So this could also be a valuable input going into a software safety analysis. So I created this one presentation, one slide, just to give an overall attribute on. So this has already been explained. So this is just to give one-page summary of everything that was explained until now. So this is pretty much like a self-explanatory. Okay, now let's get into a practical example of taking a requirement and having to do a software safety analysis from where we start to where we end up, and how we're going to make some valuable input to our software safety concept. So let's take an example here. So this is a requirement which is just made up. So let's say there is a limiter in activation. So let's say, so this is a requirement coming from a radar point of view. So regarding AB brake deceleration. So let's say there is a limiter in activation, and it says basically take certain value from certain ECU. So and this means that certain input signal must be taken from one part to another into your software. So what sort of, so this is the requirement. So in the requirement, it is talking something about AB brake deceleration request signal. So this is what it's supposed to happen. So from your software has to retrieve certain input signal from different ECU. So what sort of failure is possible within this small feature within your software? So from the failure mode guide words, so we have, it is possible that there could be no signal retrieval at all. And it is also possible that it could be too late retrieval, and it could also be possible like too early retrieval, where it affects in terms of data corruption, or even in terms of false positivity of your actuation of your function. So those are the three failure modes that is possible during this feature. And now, due to this failures, what is the negative effect? So this is where the column K comes into picture, and where we talk about effect on the output signal. So effect on the output signal is, it is either that your data itself is not retrieved, so you don't know what is the AB brake deceleration value, or it could be possible that whatever the value that you have gotten now, your software, the obsolete value will be persisting in your software. It is possible like that. So now let's connect this to system and vehicle level, and what sort of safety goal it could possibly violate. So due to too late or no signal at all, so in this the brake, so ideally the limitation should be within certain range of so the feature should have been limited to 0 to minus 3.5 meter per second square, because you don't know what is the value of your brake deceleration. You don't know how much deceleration you have to do. So in this case, the limitation, whatever it has to be between 0 to minus 3.5 meter per second square, it doesn't happen. So if you link this to a safety goal, it is possible that you will have a no deceleration or too low brake deceleration. So that is a safety goal that will be violated. Too low brake torque or no brake torque at all. So now we understood the analysis, what sort of safety goal it is violating. So the next part would be to define some sort of mitigation strategy. So the problem here was no signal or too late signal. So in the event of no signal or too late signal, anyway, we already have certain timeout monitoring which says there is no signal or too late signal. So the sort of value addition that can go into safety concept, taking this example, is that if in the event of no signal or too late signal, we can have a requirement that limits the brake deceleration to minus 3 point. Why can't we just hard code a requirement with minus 3.5 meter per second square? So this is a sort of requirement value addition that can go into a software safety analysis, from the software safety analysis to software safety concept. I hope this was useful, this example. So until now, what we discussed is all regarding what is the motivation, where we start, what are the inputs, what is the approach, and we took an actual example. And the last part is also to talk about what sort of value addition in detail I want to talk. So the first thing would be you actually get to know what sort of failure is possible within your software safety concepts that will violate your safety goal. So that is the first thing that you get to know, and the second thing is which one is critical of it, and how. And the second part will be how do you mitigate this. So the mitigation would be in terms of two things. One is you can define test measures for each failure modes and find out whether whatever the test measures, whatever the requirements is effective or not, whether there is certain sort of inconsistency or not. So how do you find that out is once the test is failing or not with respect to safe direction, the error reaction, what we defined, that means that we don't have the test measure, our software is not robust enough. In this event, what we have to do is we have to implement certain more safety mechanisms or certain more safety requirements in general. So in that way, you can actually make validation to your safety concept. So the last thing would be to talk about the summary. So this is pretty much all that I've talked until now. Identification of failure modes to identifying what sort of effect on the output is possible, and then link that to a software safety concept, then system safety concept, then the safety goals. And the second part would be to have a mitigation strategy in terms of test measures and software safety mechanisms and measures, how you can define. So the last thing I would like to say here is so all of this is a theoretical way of defining an approach and doing analysis. But what is the next step to this software safety analysis? So all of this is a qualitative analysis right now. So if it is possible to come up with a quantification of this entire process, that would be much more of a value addition as well. So that would be the scope for the further work. And if it is possible to automate, that is also another further scope for the work. So with that being said, I hope I've explained all the three things that I started out before I started my talking. So if there are any questions, I'd like to take it now. Thank you so much for your attention until now.
Hello. Yes, it was really wonderful session, and many learning must be to the participant and audience. So now we started getting the question from, one question is from Manohar from slide 6. If you can see the question in the right green box, is it a check effectiveness of requirement or safety mechanism?
So it could be both. For example, so I already mentioned, so you have to write test measures for failure mode. Then you give failure mode to what, whether it is input signal or the requirement. So if you give the failure modes to this input signal or the requirement, then it depends. It could be for both requirement or the safety mechanism itself. So majorly I would say, because we are giving all the test measures and the failure modes to requirement, so it would be directly to the requirement. In this way, we can find out what sort of insufficiency is there within the safety requirement what we have been specifying. So and we'll be able to find out if something else is necessary. I hope that answered Manohar's question. Okay, I can see. Yeah, I can see the next question. So, so what Manohar has just seen is an inductive approach. So so his question is it also possible to have a deductive approach from the software level? Yes, it is possible. So like I mentioned from ISO 26262, so there are guidelines from where you begin and where you end. It is possible you can have inductive and deductive approach as well. So if you want to take from the deductive approach, you can start from your safety goal or your software safety requirement, and then you can identify what sort of critical failure is possible at the output level. Then you can go whether this is a processing failure, then input failure, then you can still find out the cause, whether it is input or processing. And yes, it is possible to have the deductive approach as well.
Yeah, there was one more question from Ashwini. How the safety, the software safety analysis can take it up.
Yes. So the question is, software safety analysis, how is it different from your software FMEA? Okay. So there isn't much difference. So whatever approach I gave right now, it is very, very similar to your software FMEA, except the part is that we try to give failure modes to your requirements. But in case of your software FMEA, it's slightly different approach. But it is an inductive approach, like Manor already mentioned in his question. So yeah, it is very similar to your FMEA, but we don't again quantify here.
Hello.
Yes, Deepti, I can hear.
Yeah. Yeah.
So we have another question.
Okay.
Are software FMEAs required for all ASIL levels? Yes, I would say yes. I wouldn't say software FMEA in particular. I would say software safety analysis is a requirement. So ISO 26262 from second edition onwards, they actually mandate to do some sort of software safety analysis. So this could again be software safety in terms of FMEA or in terms of FTA or inductive approach, deductive approach. It is possible. So I would say yes.
Hello.
Yes, Deepti, yeah. So the next question is, considering all the requirements to analyze individually might be time consuming. Instead, can't we take architectural elements as requirement allocation and should be covered as part of architectural verification? Yes, I would agree with that. So actually we did an analysis for like around 1,000 requirements, and which took a lot of time. It is possible to do at the architecture level as well. So when we started out doing this software safety analysis, it was less known. So the competency was comparatively low. But it is always good that we're going to do something and then we actually optimize and improve the processes as well. So the next question is software FMEA performed on mixed ASIL level system? Yes, it is possible to do that as well. So if you're having a mixed ASIL level system, you can do both software safety analysis and FFI, like Varad and Abhay was mentioning earlier. But if you're doing a software safety analysis for a mixed ASIL design, is that the test measures, the safety mechanism, all of that changes slightly, and it depends on the recommendation of different types of test measures and different types of test deriving methods for different ASILs, and different safety mechanisms and different safety measures for different ASILs. Yes, it is. I would say yes, it is necessary to do mixed ASIL design software safety analysis as well. So the next question is slide 8 talks to start analysis on requirements, but slide 9 talks about components under analysis. Can you clearly explain at what level this analysis approach is aimed at? Okay, so this is aimed to do at the requirement level. So ISO 26262 actually says it is good idea to do at the software architecture level, but it is also possible to do at the requirement level, because software the requirements itself is further going to get translated into requirements. So I already showed in my presentation where from the guidelines of ISO 26262, you can start from requirements as well. Then there is architecture which gets translated into. So you can do at architecture level or at the requirement level. So what we did in our project was at the requirement level. Okay, the next question is, can we have quantitative analysis at the software level? Yeah, that's a good question actually. So how do you, the question is, the problem is that how do you quantify systematic errors? So what sort of quantification ideas you can come up with it? So that is still an open point. We are still working on it. So like I said, that is next step for whatever we are trying to do here. Next question is, what is the recommendation points to take care for third-party software during software safety analysis? Yeah, this is actually a good question. So this is something that I have not thought through until now. So if you have a third-party software, you don't know what sort of mechanisms they have. You don't know what sort of requirements they have. So all the best thing that can be possible from a third-party software is that you have to take some sort of a confirmation from the third-party software whether what they're going to give is with respect to SLB, or maybe you can have some sort of meetings where they present what sort of so they can also do software safety analysis, which could be an evidence of what they have done in this for this software safety concept. So that is something that can be arranged in terms of meeting, and this possible. Okay. What is the recommendation to perform software safety analysis? Consider only input signal, consider only output signal, both input, output signal. So I would say you can, so if you are doing an inductive approach, you can consider both input signal and processing failures within a software. So if you are doing like deductive approach, it is good idea to start considering output signal. So you can consider from your software what are the safety critical outputs that are going, and you can derive down to causes of how the input failures are happening, and that is a good way to do it. And we have one more question. What is the reason it is not required to perform spatial analysis? Okay. So this global variable and static variable spatial analysis is done much more at the freedom from interference and the mixed ASIL level. So this is something that we don't go in depth in software safety analysis, because the approach we are doing here is with respect to requirements, and it is not possible every time to go in depth as to say global and static variable corruption and so on. Okay, we have further more questions. If compilation stops, doesn't it a safety mechanism, column K and column N are same? It is not clear why we need a safety mechanism. Okay, this is probably regarding the first requirement from what I showed. So actually here the compilation stopping, if you don't have a limiter active, the compilation stopping itself acts as a safety mechanism here. So the reason why is, so if the limiter is active, is not active, then it is not necessary to limit within certain range. In this way, the compilation will stop in order to limit the value between 0 to minus 3.5 meter per second square. So this is a safety mechanism if the limiter is not active. It is not when it is active. So
Hello.
yes, Deepti.
Yeah, so we have now a limited time to take questions. I would like to encourage people to use the chat function and meet function in the by the platform providers. So it is better to connect with that. So now we have time to go for the keynote address. So I would like to say here is the whole agenda of the session was met, and very excellent papers present by our presenter, and it is really indeed a very much fruitful and interactive. Participation is also very excellent. So I again request participant to chat with presenter for any further question, and this chat function will be live for more some time. So use the networking opportunity. So now with this, I would like you all request to move towards the next session of keynote address by Ms. A.R. Padmaja, Vice President Engineering, Vehicle Safety System, Bosch Limited. So it is there at a plenary session. You can log in through plenary session and learn from Padmaja about the functional safety. So once again, thank you all, and see you soon. Thanks a lot. Yeah.
Thank you so much, Ms. Deepti, for giving a valuable time to chair this wonderful session.
Thank you, sir.
For this wonderful session, and we know we are keeping you in your chair for quite some time now. So you can take a 5-minute break. You can just go for a walk, and be sure to be back in the platform by 4:30, because as Ms. Deepti said, we have the keynote of Ms. Padmaja. So see you soon then. Thank you. Bye.
Thank you very much.